Imagine standing at the edge of existence, a place where the laws of physics crack like thin ice, a region of space where not even light escapes. You are about to cross into a black hole. But this isn't from a distance, not a telescope's eye view. This is first person. What would it feel like to fall inside? What would you see? How long would you survive? Would you even die at all? This isn't science fiction. This is theoretical physics taken to its breathtaking extreme. Buckle up, reality is about to get very weird. Chapter 1. Approach. You're on a one-way trip. Behind you, the stars shine, distant and cold, silent witnesses to your descent. Your breathing is calm but shallow, each inhale echoing inside your helmet like a countdown. The onboard systems hum with a sterile rhythm, but outside, nothing stirs. Your chest tightens not from gravity, but from awe. The vastness ahead is paralyzing, a shadow darker than space itself. Somewhere deep in your mind, instinct screams. Every fiber of your body knows you should not be here, but curiosity overrules fear, and still you drift closer. Ahead, the black hole looms like an open wound in space, a sphere of perfect darkness. It doesn't suck things in like a vacuum cleaner. Instead, its gravity is so strong that space itself falls inward. As you approach, things start to stretch visually and physically. Distant starlight begins to bend. The black hole warps the sky like a lens. Time seems to slow. You feel no pain, no jolt, but the horizon ahead is the point of no return. This is the event horizon. Chapter 2. Crossing the horizon. Here, the laws of physics start to crumble. To a distant observer, you appear frozen in time at the edge, but from your perspective, you keep going. Strangely, you feel normal, the same. You pass the event horizon, and something wild happens. You can now see the entire universe behind you. It's not in front. It's above, behind, smeared across the curve of space. You're falling inward, but the outside is folding over your head. Light from the universe is being bent around the black hole's edge, giving you a final glimpse of everything that was. This is not darkness. It's distortion. Chapter 3. Spaghettification. Closer to the center, gravity stops being gentle. You are pulled headfirst. Your feet feel more gravity than your head. The difference becomes immense. You begin to stretch like spaghetti, your atoms separate. Your body is elongated. Time itself begins to stutter, seconds feel like minutes, and yet the moment seems endless. Reality no longer obeys the clock, not violently, but completely. And yet, you're not in pain. In fact, your brain can't even register what's happening fast enough. You are information now, being drawn into a singular point of infinite density. Chapter 4. Inside the singularity. No science has fully modeled what lies at the core. We call it a singularity, a place where density is infinite and the known laws of the universe collapse. You are no longer falling. There is no direction. Time doesn't move forward or backward. It ceases. And yet, something exists. Are you a pattern now? A ripple of probability? A new beginning? Some physicists believe the singularity connects to other universes' white holes, baby universes, or wormholes. Inside, you are data, your entire history encoded in the fold of space. Chapter 5: Hawking Radiation and Evaporation. You're gone from the visible universe, but the black hole isn't immortal. Hawking radiation slowly leaks mass from the hole, particle by particle. Over trillions of years, it shrinks, fades, disappears. Where do you go? Does your information come back, or is it lost forever? This is the information paradox, and it's one of the biggest unsolved mysteries in science. Some think information is never lost, that you still exist somehow in the echo of quantum fields. Chapter 6: Theories Beyond. Some physicists propose bold ideas. That black holes store information on their surface, like a hologram. That our universe began in a black hole in another dimension. That every black hole births a new universe, slightly different from ours. If true, falling into a black hole is not an ending. It's a transfer. Chapter 7: Perspective. To those left behind, you're gone, vaporized, crushed. But from your viewpoint, time dilates. The universe outside seems to speed up. You could see the birth and death of stars, the end of galaxies. Your fall stretches into eternity. In that way, you become timeless, a ghost in the geometry of space. Chapter 8: Could we visit a black hole? Technically, maybe. Practically, not yet. To survive the tidal forces, you'd need a supermassive black hole millions of times the mass of the Sun. One example is Sagittarius A, the black hole at the center of our galaxy, which has a mass of about 4 million suns. Even more massive is TUN 618, a supermassive black hole in a distant quasar, estimated to be over 60 billion solar masses. In these giants, the gravitational gradient at the event horizon is surprisingly gentle, allowing a hypothetical traveler to cross without immediate destruction, of times the mass of the Sun. In such giants, the gravity gradient is weaker at the event horizon. You could cross it without being torn apart, at least initially. But communication, escape, those are impossible. A journey into a black hole is one way, forever. Chapter 9: Why It Matters. Black holes are nature's stress test. They're not just theoretical curiosities, they're being studied today with real instruments like LIGO, which detects gravitational waves from black hole mergers, and the Event Horizon Telescope, which captured the first direct image of a black hole's shadow in 2019. They break our theories, our equations, our understanding. But they also point the way forward. They teach us that space is not static, that time is not absolute, that reality is deeper, stranger, and more interconnected than we ever imagined. To study them is to study the edge of what's real. Conclusion: the fall never ends. In fiction, black holes are portals of destruction. In reality, they are invitations to confront the limits of understanding. To peer into the abyss is to confront our deepest questions. Where does it all go? What remains of us? And could something stranger than death be waiting on the other side? In science, they're laboratories of truth. We may never truly see inside, but through mathematics, imagination, and quantum theory we can fall. And in that fall, we glimpse the raw machinery of the cosmos. For centuries, Neptune was just a blue dot in the void. Distant, cold, silent. But then, something happened. In a routine observation by the James Webb Space Telescope, astronomers noticed something unusual. A flare, an energy spike, a signal that something massive had hit Neptune. The outer solar system had stirred, and what followed changed everything we thought we knew. This isn't science fiction. This is a real cosmic event, an impact in the dark outskirts of our planetary neighborhood. Let's rewind. Let's find out what happened, what it means, and how one explosion on Neptune might reveal secrets about the solar system and our future. The silent giant. Neptune orbits 4.5 billion kilometers from the Sun. It's an ice giant wrapped in methane blue clouds, circled by faint rings, and whipped by winds faster than sound. For decades, it's been largely ignored. Too far, too faint, too quiet. Unlike Jupiter with its great red spot, or Saturn with its magnificent rings, Neptune lurked on the edge of attention. Until James Webb looked closer. The flare. Webb was scanning Neptune's southern hemisphere for magnetic activity and cloud behavior. That's when it happened, an unexpected spike in infrared radiation. Sharp, bright, instantaneous. The telescope wasn't even aimed to catch a collision, but it caught one. Neptune's cloud bands, normally smooth and slow shifting, showed a circular disruption. Like a shock wave, something massive had struck it. The impact. Infrared analysis showed thermal gradients, heat released by something slamming into the atmosphere. The estimated object, a rogue trans-Neptunian object, an icy body about 40 kilometers across. No crater. Of course, Neptune is gas and ice, but the energy released sent spirals through its clouds. A heat signature lingered. The planet's reflective brightness albedo changed. For a planet once thought too far to matter, it suddenly mattered a lot. Fallout and mystery. Debris from the impactor hovered in Neptune's upper atmosphere, a dusty arc, visible in infrared and visible light. Particles swirled with the jet streams. Spectral scans showed something stranger: nitrogen compounds and hydrocarbons not normally found in such concentrations. Was this residue from the impactor? Or had Neptune's chemistry been jolted into change? The magnetic shiver. Neptune's magnetic field is weird to begin with, tilted, unstable, and offset from the core. After the collision, it got stranger. Flux in charged particles increased. Magnetic waves rippled across the field. Something had nudged the planet's deep interior. Could this mean that planetary impacts still influence internal dynamo systems? The bigger picture. The impact was big, but the implications are bigger. For years, astronomers believed massive collisions like this were relics of the early solar system. But this happened now. This suggests the outer solar system is still a dynamic, dangerous place. If this 40 km object had hit Earth, it would have been catastrophic. How many more such objects are out there? How many close calls go unseen? Why we almost missed it. Webb wasn't looking for this. Ground-based telescopes missed it. No visible flash was caught. If not for a scheduled infrared scan, this impact would have gone unnoticed, swallowed by Neptune's churning blue atmosphere. The lesson? We're blind to much of what happens on the edge of our system. It's a cosmic blind spot. What's next? Astronomers are now reprioritizing outer solar system observation campaigns. Hubble and Earth-based telescopes are being retasked to monitor Neptune. The European Southern Observatory has planned follow-up spectroscopic analysis. Meanwhile, theorists are rerunning models of planetary formation. Maybe the solar system is still sorting itself out. The collision on Neptune wasn't just an isolated event. It was a reminder. The outer solar system is alive, active, and watching it can teach us not just about ice giants, but about how worlds form, change, and survive. One impact, one ripple, and suddenly, the quietest planet is shouting through the dark. James Webb saw something that breaks the universe. The impossible image. In July 2022, the James Webb Space Telescope sent back its first full images. Scientists were prepared for beauty, precision, detail. They were not prepared for what was inside them. Galaxies that shouldn't exist. Structures too old, too large, too early. The deeper we looked, the more the universe broke the rules. The data isn't wrong. The telescope isn't malfunctioning. So what's going on? This is the story of an image that shook modern cosmology and what it might mean for the beginning of everything. A telescope that sees back in time. James Webb isn't just a telescope. It's a time machine. By capturing infrared light, it can see objects that are billions of light years away and billions of years in the past. The first galaxies. The infant universe, the era when stars were just beginning to form. Webb was designed to confirm our best models of how the universe began. Instead, it might be unraveling them. The galaxies that shouldn't be there. In Webb's early deep field images, researchers found galaxies that looked far too mature. Some appeared to be as massive as the Milky Way, yet they formed just 300 million years after the Big Bang. According to current theory, that's impossible. There wasn't enough time. Galaxies should grow slowly from small clouds of matter, merging and evolving. But these, they were already massive, already spinning, already complex. Like walking into a maternity ward and finding a fully grown adult. It doesn't make sense. Unless our understanding is wrong. The broken cosmic timeline. These early galaxies aren't rare mistakes. Webb keeps finding more of them. One paper described them as uncomfortably abundant, which forces a terrifying possibility. Our entire timeline of the early universe may be off. That would mean the Big Bang wasn't what we thought. Cosmic inflation happened differently, or the laws of physics behaved differently in the past. Any of those ideas would rewrite everything we know about reality. And it all started with a photograph. What could explain this? Theories are pouring in. Some scientists propose dark galaxies, invisible structures of dark matter forming faster than normal. Others suggest that the galaxies aren't massive, just brighter than expected, due to early black holes or population 3 stars, the first stars ever born. Another theory? We're misjudging the redshift, that we're looking at something much closer, but distorted. But none of these fully explain the number, size, or structure of what Webb sees. And the deeper it looks, the more it finds. The universe might be older than we think. One of the boldest suggestions is that the universe is much older than 13.8 billion years. That the Big Bang wasn't a single event, but just the latest in a cycle. This would support theories of a bouncing or cyclic universe, one that expands, collapses, and expands again. In that case, these early galaxies aren't anomalies. They're leftovers from the last version of reality, and we're living in a reboot. Why this changes everything. The James Webb Space Telescope was meant to confirm the Big Bang model. Instead, it's destabilizing it. That's not failure. That's discovery. Every time in history, we've improved our tools, microscopes, radios, telescopes, reality has become stranger. What Webb is showing us isn't broken data. It's a broken assumption. And the universe is stranger than we imagined. We're still at the beginning. This isn't the end of cosmology. It's the beginning of a new version. The universe has always been bigger, older, and weirder than we thought. And now, we have a mirror powerful enough to show us just how wrong we were. What Webb saw may not break the universe, but it's definitely breaking our idea of it. What happens when extreme space objects collide? The moment of impact. Space is not quiet. Not really. It hums. It crackles. It vibrates with violence. And sometimes in the cold dark, it collides, not gently, not slowly, but in bursts of energy so powerful they warp spacetime itself. Black holes, neutron stars, white dwarfs, These are the deadliest, densest objects we know, and when they meet reality bends, this video isn't just about explosions. It's about the laws of physics pushed to their limits. So what happens when the universe crashes into itself? Let's begin. The densest things in existence. First, meet the players. White dwarf stellar corpses, Earth-sized but with the mass of a sun. They're the end state of average stars like ours. Dense, stable, until they're not. Neutron stars even smaller, even heavier. Just 20 kilometers wide, but with more mass than our sun. 1 teaspoon of neutron star matter would weigh billions of tons. They spin, they pulse, they glitch. Black holes, the point of no return. Pure gravity. No surface. No bottom. Some are born from stars. Some sit at the centers of galaxies. All of them are violent by nature. But when they collide, the real story begins. White dwarf plus white dwarf, the silent supernova. 2 white dwarfs locked in a binary orbit will spiral closer over millions of years. Eventually, they merge. If their combined mass exceeds the Chandrasekhar limit about 1.4 times the mass of the Sun, something terrifying happens. They explode. Type Ia supernova, one of the brightest events in the universe. It leaves nothing behind. No neutron star. No black hole. Just pure light and expanding gas. Astronomers love these collisions. They use Type Ia supernova as standard candles to measure distance. But for the stars involved, it's oblivion. Neutron star plus neutron star, the gold forge. When 2 neutron stars collide, the universe changes. First, they spiral toward each other, warping space as they go. The dance speeds up. Time distorts. Then impact. The collision produces gravitational waves, literal ripples in the fabric of spacetime, which we can now detect thanks to LIGO and Virgo. But that's not all. These mergers create kilonovae, explosive events that forge heavy elements like gold, platinum, and uranium. That ring you wear, that satellite part, it may have been born in one of these collisions. What's left behind? Sometimes a more massive neutron star. Sometimes a black hole. Always a scar in the cosmos. Neutron star plus black hole, the silent devouring. This is not a fair fight. A neutron star approaches a black hole. It spirals in. It begins to stretch, torn by gravity. Then it vanishes. No light, no explosion, just gravitational waves and absence. The neutron star is swallowed whole. Depending on the size, it may be ripped apart, first sending out a flash of gamma rays. But usually, it simply disappears. These collisions are rare, hard to detect. But when we find them, they confirm Einstein, challenge models, and remind us of the universe's appetite. Black hole plus black hole when gravity meets itself. Two black holes don't collide like billiard balls. They merge like ghosts, like gravity consuming gravity. No light escapes, but the collision sends out a shockwave of spacetime, a gravitational roar. In 2015, we heard it. For the first time, LIGO detected the merger of two black holes 1.3 billion light-years away. Since then, we've heard dozens more. Each one a cosmic drumbeat, the result? A bigger black hole, a loss of mass turned into energy, and a permanent dent in the universe's memory. The unseen violence of space. All these collisions happen far away. They don't touch us, but they shape us. The gold in your blood, the atoms in your bones, the iron in your blood. They were made in fire infusion, in collision, in collapse. The universe isn't calm. It's catastrophic, and in that chaos, life formed. We are the ash of cosmic accidents. Collisions we haven't seen yet. There are collisions we know must happen, but we've never seen them. White dwarf plus neutron star could lead to a rare type of gamma-ray burst, neutron star plus black hole, plus another black hole, a triple merger. Mathematically predicted, never observed. Black hole with a rogue planet. No one knows what it would look like. And then, there are things we haven't even imagined. What happens when two intermediate mass black holes merge? What happens if a black hole eats a quark star, assuming they exist? We don't know. But Webb might see it, or LISA, or something that hasn't even launched yet. The sound of collision. Gravitational waves aren't just abstract ripples. They can be turned into sound when two black holes merge. They emit a chirp, a rising frequency as the orbit tightens, then a sudden cut-off. It's the most massive sound in existence. A death song. And we're just now learning how to listen. The biggest collision still to come. In 4 billion years, the Milky Way will collide with Andromeda to galaxies. Hundreds of billions of stars, massive central black holes. It won't be a fiery crash. Space is too empty, but the black holes will find each other and eventually merge. A final exhale of gravitational energy. Earth might be gone by then, but the echo will ripple across the universe. A reminder that nothing stays still. Collision is creation. We tend to fear collisions, but in space, they're not just endings. They're beginnings. Every crash reshapes the cosmos, builds heavier elements, sparks new stars, seeds planets, forges possibility. You are made of remnants, of things that hit too hard to survive. That's not destruction. That's birth. The day the sun blinks, what happens if the sun suddenly shuts off? The unthinkable. Every morning, we wake up under the same sky. We don't question it. The sun rises. The sun sets. It is the most reliable thing we know. But what if one day it didn't? What if, without warning, the sun vanished from the sky? Not gradually, not in billions of years, but now. No sunrise, no warmth, no light, just silence. How long would we survive? What would break first, the Earth or us? This is not a science fiction story. It's a real exploration of what would happen minute by minute, day by day, if the sun simply shut off. And it starts right now. The first 8 minutes. When the sun goes out, we won't notice at first. Light takes about 8 minutes and 20 seconds to reach Earth. So even if the sun disappeared instantly, we'd have 8 more minutes of normalcy. You'd be driving to work. A kid would be pouring cereal. Someone would be boarding a plane. Everything would feel fine. And then the sky would go black, not like night darker. Stars would suddenly appear where the sun used to be. No glow, no warning. Just absence. The moon would vanish too. No sunlight, no reflection. People would look up, confused. Is this an eclipse? A power outage? A cosmic prank? And then the temperature would start to fall. Day 1. Shock and shiver. Without sunlight, Earth begins to cool rapidly. In the first 24 hours, temperatures drop by a few degrees. Not apocalyptic yet, but noticeable. The sky remains pitch black, even during day. Solar panels stop working. Plants begin photosynthesis shutdown. Birds and insects are disoriented. People panic. News channels scramble to explain. Scientists appear on live streams confused, terrified, lying to look calm. Governments declare emergencies. But no one has a plan for this. By the end of day 1, the world is gripped in a kind of collective disbelief. The sun is gone, and everyone knows it. Week 1, the world freezes together. Within 7 days, Earth's average surface temperature falls to approximately 0 degrees Celsius, the freezing point of water. Equatorial regions are still above freezing, but Europe, Russia, and Canada, icy. Crops begin dying. Animals migrate aimlessly. Power grids are overloaded as people blast heaters. There's no sunrise. There's no morning. Only artificial light and fear. Governments activate emergency food reserves. NASA and ESA issue strange abstract updates. Physicists are silent. No one can explain the sun's disappearance because it defies all laws of physics. Still, the Earth keeps orbiting. That's the most unnerving part. The stars remain. The galaxy continues. Only our star is missing. Month 1. Exodus and adaptation. After 1 month, the average global temperature drops to approximately minus 17 degrees Celsius, just 1 degree above the Fahrenheit freezing point. Humanity adapts, as it always does. Entire populations begin migrating underground. Mines, bunkers, subway systems, anything that holds warmth. Above ground, the world is abandoned. Cars freeze, buildings crack, oceans begin to frost over, starting from the poles. Most plants are dead. Agriculture is over. Photosynthesis has stopped. The only food is what we had stored and what we can synthesize. The rich escape to deep shelters. The rest try. Some build underground cities. Some go mobile diesel-powered Arctic convoys. And still, no one knows why this happened. Year 1. The Ice Age returns. 1 year without the sun. The average surface temperature is now approximately minus 73 degrees Celsius, which is 100 degrees below freezing on the Fahrenheit scale. Earth is frozen. The oceans have crusted over with thick ice, though liquid water still exists far below. The atmosphere begins to condense. Nitrogen and oxygen freeze out of the sky in the coldest places. Most of humanity is gone. A few survive near geothermal vents, nuclear plants, deep biospheres built in panic. We live like extremophiles in the warmth of Earth's belly, not its skin. Animals? Most are extinct. Plants? Dead. Civilization? A ghost. The dark mirror of time. Years pass. Earth no longer has seasons or days, only temperature gradients. Geothermal power and nuclear energy keep small colonies alive, but they shrink with every generation. History books become sacred. The memory of the sun becomes legend, a myth. Some think the sun was a god. Others think it was a lie. New religions emerge: sun cults, darkness cults. Some worship heat, some the cold. Some reject the past entirely. The few surviving scientists try to keep data alive. They still monitor space, using what's left of their energy. But no signal comes. The sun is still gone. If physics breaks, what else does? The disappearance of the sun violates everything we understand about physics. Stars don't just turn off. They can explode, collapse, transform, but not vanish. This means either something beyond our comprehension occurred, or someone did it. Some theories emerge. We're in a simulation, and the sun was deactivated. A black hole swallowed it silently. Alien engineering. A Dyson-level event. None of it fits. Whatever happened, it wasn't natural, and it wasn't random. That thought keeps survivors awake more than the cold. A planet adrift. Without the sun's gravity, Earth's orbit is disrupted. But momentum carries us. For now, we drift in a straight line outward. Away from the solar system, the stars shift. Other planets are gone. Their orbits spiraled, collided, or wandered off. Earth is a rogue planet, now a cold, dark marble falling forever. Sometimes auroras ripple from internal magnetic activity. Sometimes distant stars shine through the ice. But mostly, there's just dark. No day, no night, no future. The final generation. Eventually, energy runs out. The last nuclear fuel is spent. Geothermal vents shift. The final humans or something descended from them freeze beneath miles of ice. They go out not with fire, but with silence. The earth becomes a frozen tomb, a wandering relic of life that once basked in warmth. And somewhere, light still travels from the moment the sun went dark. 8 minutes of sunlight caught in motion, heading outward into deep space, carrying with it the last image of Earth as it was, warm, alive, unaware. Why this story matters. This didn't happen. Not yet. But it could. Because the sun isn't just a light bulb in the sky. It is life. It is law. It is everything. And we treat it as permanent when it isn't. This story matters not because it's true, but because it's possible. Because we should never take the sky for granted. Because every sunrise is a miracle. And because the moment it blinks, we blink with it. Into the nothing. Imagine no space, no time, no light, no matter. Nothing. Not emptiness, not a vacuum, not darkness, but the complete absence of existence. Yet somehow from that came everything. The stars, the galaxies, the laws of physics, even your thoughts right now. How is it possible that something as complex and ordered as our universe could come from nothing? This isn't just a philosophical question. It's a scientific one. And at the front lines of that question is quantum physics, a framework so strange, it makes nothing one of the most complicated ideas in all of science. In this journey, we'll explore what physicists mean by nothing, how quantum fluctuations can create particles from an empty space, whether the universe emerged from a quantum void, and why this question reshapes our understanding of existence itself. Let's fall into the void, redefining nothing. In everyday language, nothing is simple. It's the absence of stuff. An empty cup, a blank page, but in physics, especially quantum physics, nothing is far from empty. Even what we consider a vacuum, a region with no particles, no radiation, no atoms, is seething with activity. Welcome to quantum vacuum. Here, virtual particles constantly appear and vanish. Space is filled with fields, Higgs fields, electromagnetic fields, gravitational fields, all fluctuating at quantum levels. At absolute zero, when thermal motion stops, quantum motion continues. Why? Because of the Heisenberg uncertainty principle. You can't simultaneously know the exact energy and position of a system. So even nothing must wiggle. This quantum jitter isn't just theoretical. It's measurable. It's the reason for the Casimir effect, where two uncharged plates in a vacuum attract each other thanks to fluctuations in the vacuum energy. So, the first lesson: nothing is not nothing. It's a dynamic stage buzzing with potential. Virtual particles and the birth of matter. Inside this energetic vacuum, virtual particles constantly pop in and out of existence. These aren't particles in the traditional sense. They don't follow the rules of real particles. They're fleeting disturbances in quantum fields, allowed to exist only briefly due to energy-time uncertainty. Sometimes these pairs annihilate instantly, but under the right conditions, like near a black hole's event horizon, one particle can fall in while the other escapes. This process, proposed by Stephen Hawking, leads to Hawking radiation black holes slowly evaporating over time. It proves that quantum effects at the edge of nothingness can generate real, observable consequences. If that can happen near a black hole, could it happen on a universal scale? Could the universe emerge from nothing? Here's where things get wild. Some cosmologists propose that the universe itself could have emerged from a quantum fluctuation, a spontaneous blip in the vacuum energy of a quantum field. Lawrence Krauss famously wrote, "A universe from nothing," suggesting that if you have quantum laws and gravity, you don't need a creator, you just need instability in the void. But critics argue, laws themselves are something. So where did they come from? Others, like Stephen Hawking and James Hartle, suggest that the universe had no boundary, it didn't begin in time, but emerged as a closed, self-contained system. Inflationary cosmology takes this further. Tiny fluctuations in the early universe expanded exponentially, creating the structured cosmos we see today. So perhaps nothing isn't a clean slate, it's a bubbling cauldron of potential. Nothing, multiverse, and the anthropic principle. If something can come from nothing once, could it happen again? Welcome to the multiverse. Some theories suggest that our universe is just one of many, each popping into existence from quantum fluctuations in a meta-reality. Each universe could have different laws, constants, or dimensions. The anthropic principle says we find ourselves in this universe because it's one of the few where life is possible. In most, conditions wouldn't allow galaxies, planets, or consciousness. It's a controversial idea. Some see it as giving up on deeper explanations. Others see it as the only way to make sense of the fine-tuning of our universe. Is nothing the seedbed of infinite universes? Or is the multiverse just a placeholder for what we don't yet understand? The psychology of nothingness. We're hardwired to think in terms of things. So when science tells us that the fabric of reality may emerge from non-being, it challenges not just our physics, but our intuition. Ancient philosophers grappled with the void. In modern times, Nietzsche, Heidegger, Sartre, they all asked what it means to exist at all. Quantum physics now brings those questions into measurable reality. Maybe consciousness itself is a byproduct of quantum complexity arising from the vacuum. Maybe the brain is a fluctuation in space-time. Dreaming it exists, maybe the universe is not a thing, but a question unfolding. What we know and still don't. We've detected vacuum energy. We've measured virtual particles. We've modeled quantum cosmology, but we still don't have a complete theory of quantum gravity. We don't know how time really began. We don't know what underlies the fields themselves. The Planck scale 1035 meters is where quantum mechanics and general relativity crash. It's where our current tools break. To understand true nothingness, we may need a new paradigm: string theory, loop quantum gravity, emergent spacetime, or something yet unimagined. Until then, we circle the void, knowing it's not empty, just waiting. Until then, we circle the void, knowing it's not empty, just waiting. The power of nothing. The greatest mystery of the universe may be that it shouldn't exist at all, but it does, and maybe, just maybe, it came from nothing. But not the kind of nothing you imagine, not silence or darkness, but a seething, quantum field of uncertainty, ready to erupt into stars, atoms, and life. So next time you stare into the night sky, remember, the stars might not be the greatest miracle, the nothing between them might be. Like this journey into the void. Subscribe, share, and join us as we keep asking the biggest questions in the universe.